Hey DZone, we're here at All Things Open 2015 in Raleigh, and I'm here with Brandon Phillips, the CTO of CoreOS, a very exciting project. We're going to talk about containers, about Docker, about CoreOS, and distributed systems and things like that. So Brandon, can you just introduce yourself?
Sure. So I'm Brandon Phillips. I'm the CTO and co-founder of CoreOS, and we build a lot of this stuff to help people have this kind of Google-like infrastructure. And this has come out of all this container ecosystem kind of explosion. Is this concept of, I have containers, this is cool, it gives me independence from the underlying operating system, move my app around, but now I can move my app around, so I want to do more interesting things. I want to kind of build a really fault-tolerant, easy-to-manage infrastructure, very much like we've seen in Google and other large internet infrastructure companies. And so we've been building, distributed databases and operating systems and all sorts of tooling in the open source to kind of enable this new way of building infrastructure.
Cool. And I guess one of the exciting things about containers, of course, is that the developers don't have to worry a lot about operating system level issues. But you come from a systems programming background, so you understand how this all fits together.
Right. Yeah. So my background. I worked at Rackspace. We were building a large distributed monitoring system focused on, helping our operations people understand from an internet perspective how their application is performing and whether it's up or healthy. And going through that experience of trying to run an application across 5 data centers, we figured out how important operating system consistency is, deployment consistency is, making it really easy to roll forward and roll back deployments of the software. And these were all things that we had to slowly over time build tooling and processes around, because there were no really good off-the-shelf tools that you could just kind of take and consume and have this style of infrastructure. So through a number of bumps, bruises, scars, and paper cuts, kind of generated some opinions on how this stuff should work. And then before that, I was working at SUSE, putting together operating systems. And so, I wanted to start, and my co-founder Alex Colby and I wanted to start from the very bottom and kind of fix the consistency and deployment challenges that we saw around the operating system, and then move up the stack through containers and distributed systems. And so that's kind of been the journey we're on in the last 2.5 years, is taking those bumps and bruises from working on big distributed systems and building operating systems and tools to make that a better experience.
Right, no, and that makes sense. And I guess one of the exciting things about containers, of course, is that instead of having everything as like a house of cards that gets down to the actual hardware drivers, there's a layer, like a clean cut, above which you no longer have to actually start to think about those things at all, because everything is inside your container, right? Right.
Yeah, so the interesting thing that has happened with containers, like that clean cut that is actually happening, is we've recognized the Linux, like a Unix process is a fairly well understood thing. It's something that we can debug, it's introspect, it's something that we can put resource limits around, etc. And so that's kind of been an abstraction of compute for decades. And so what containers actually do is they say that abstraction of compute, well, all the libraries and binaries and runtimes to actually support that process, where that process gets its running code, we're going to package those up into individual silos that can run on top of a single Linux kernel, but they bring along with it all the user space bits that they need. And so that's been kind of the big shift. Is before it's like this muddled mesh of the operating system handles some of the stuff like my Java runtime or my Python runtime, and then I just put in the bytecode or the Python script that I want to run, and it makes it really hard to be moving from one version of the runtime to the next. It makes it hard to have consistency, because inevitably you're going to be like, well, this code requires Java 7, but I have this Java 6 app and I don't want to risk it. And you just end up in all these situations where if you cleanly separate, you end up in a better deployment situation. You don't have this, all things bad come out of uncertainty, right? Like, people panic under uncertainty, they get frozen by uncertainty, and so having the certainty that, I packaged my app this one way and it worked, and then I just have to rely on the operating system providing that level of abstraction, frees up a lot of just mental capacity.
Right, and it's actually just like staying in user space is massively low stress compared to touching somewhere on kernel space.
Oh yeah, like you do not want to be in kernel space. That's where my career started, and it's really hard. You end up in a spot where I worked on this this hardware platform Intel sent me, and it I had 2 bytes of data as a debugging tool, and so I was doing kernel bring up code, and at any time my only debug message could be these 2 bytes of data that displayed on the front of the panel. So it's much more fun. It's much more fun to be able to do print line and dump, plethora of bytes of data.
Right. Otherwise, you're like, let me poke it there. Oh, let me poke it there, and then 50 times later, you're like, maybe this is it.
Right. Yeah.
Yeah. And one of the great things about working in a managed environment is that you can get a nice trace. You can understand the debugging problems pretty well. So as long as I guess you're staying in that, again, debugging. So one of the issues that people talk about when they talk about containerization is the problem of debugging a system that uses multiple containers, of getting the introspection of the containers and thinking in terms of processes, while now thinking about your whole application's interprocess communication and so forth.
Right.
Can you talk a little bit about how to address that problem? Is that an issue? Is that something that's getting solved?
So this is actually, I think, an improvement over what we've had with like IaaS or virtual machines. So with virtual machines, we kind of have this concept of like one virtual machine that handles one logical piece of our application. And like you generate a golden image, and then that golden image gets shipped across, and you spin up more as you need more capacity. The nice thing about containers actually is I'm able to install debugging tools as I need them on the machine, and then I can just point at the process ID just like I did before, and do an S trace or do an L trace, and like start to introspect using tools that I'm familiar with. Whereas on the VM, I may have baked a golden image, and then like GDB wasn't installed there, TCP dump wasn't installed. Then I have to kind of, what do? It's a golden image, it's read-only, I'm not supposed to manipulate it. So that's kind of the nice thing about containers, is that the golden image is at a level where we actually have tools to debug those things, because they're a process. Now, granted, it is more complicated than before, because we do have these kind of complex file system layouts and networking setups, etc. But that also brings with it new opportunities to have better security primitives in place. It brings in opportunities of having better separation of concerns, so we can upgrade individual components separately. So it's one of those things where kind of having this muddled mess of our operating system I think we've kind of learned that lesson. It's really hard to manage, manage upgrades, manage the consistency of the application deployment infrastructure. So yes, it's slightly harder than just that big single machine image sort of mindset, but it does have advantages over some of the other attempts that we've had at kind of breaking services apart so they're independent.
Right. Now, it's still, to me, conceptually harder once you have like a child in its own system, like a Shroot or something like that.
Yeah.
It's always harder to reverse that, or in like a paging system to reverse that kind of mapping.
Yeah.
Is that fair? Are there tools that are developing around this that make it easier, or techniques that you can suggest? Or?
Yeah. So kind of like getting into the container and debugging and like understanding the actually operational side of the container is more challenging. There are tools being developed. I've seen really cool prototypes on Google's Kubernetes where they will actually they'll launch another container next to your container that's running, and that container will have GDB, and then you attach that over a TCP socket. So you can actually say like, my container's running, launch a GDB inside of that container so that I can like attach to a process. And so one nice thing about containers is that we actually have the opportunity to kind of have these tools being built that are general purpose tools that can be hit against any application, and it actually integrates at the cluster multi-machine level. So instead of SSHing into the box and then installing GDB, etc., and be like, you know what, choose one of these things behind my load balancer, take it out of the load balancer and attach a GDB for me, and like I'll have an interactive session.
Tap in there.
Yeah.
Nice.
So it's kind of cool. There's like, we have the opportunity to have less like digging around through the low level details and more opportunity to say, make high level debugging decisions. And you see this with products like Weaveworks has this product called WeaveScope that gives you like a full system view of the network. And then Sysdig is this tool that's emerged that's container aware and lets you like gather metrics from each individual container and kind of get an understanding of what each container is doing at a system level. So I think there's a lot of cool opportunity that's opened up through this space.
It's like system-oriented debugging or something like that.
Right.
Service-oriented debugging.
Yeah. Exactly.
Cool. So actually, this leads me a little bit to like, so you talked about you used to work on kernel level stuff.
Right.
and you've been talking a little bit about like distributed systems and those kinds of problems. Now, how did you guys decide to come up with CoreOS, which I guess is a fork of ChromeOS? Like, what problems did it led you to that point? What solution you have?
Yeah, so one of the things that we focus on, two of the things are consistency and security. And this all comes back to the idea that no software is ever going to be secure. Like, the most secure software will be the ones that never communicate to the outside world. They're just forever, calculating the Fibonacci sequence and writing out to a dot matrix printer, right? Like perfectly secure software. So the more interesting software is going to interact with the real world. And the real world is unpredictable, and there's always going to be somebody who's trying to attack, any public-facing system. And so the only protection you have is to create systems whereby you can update them, and that you can update them with confidence that if inevitably you push some bad code, you're able to roll them back. And so our operating systems have made that really, really hard to kind of roll out a new version of the OS and then roll it back if something goes wrong. Package managers, which we've relied on and have been greatly, they are part of the reason Linux has been so popular, is that you, at your fingertips, have tens of thousands of packages. The problem with package managers is that after I do my apt-get install or my apt-get upgrade, my system is in a very inconsistent state from the moment I press enter to when it actually exits zero. Like, files are moving around, configuration files are being rewritten, etc. And so with CoreOS, we wanted to build a system that was very consistent and then allowed for this secure updating, or this auto-updating.
Like atomically?
Atomic auto-updates of the operating system were our goals.
Right.
And so the way you actually do that is very similar to like fancy hardware, like expensive Cisco routers and stuff. You have 2 copies of the OS at any time, and you upgrade from one to the other atomically, and then
next reboot you switch over.
Exactly, right. And then we do all this this fun stuff in the bootloader. I mean, fun in the sense that we're systems engineer and we enjoy writing bootloader code, but all this stuff to detect whether the system actually successfully updated, and if not, then roll back. And so from ChromeOS, so CoreOS started as a fork of ChromeOS, not as a fork of ChromeOS like we have a browser and that sort of stuff, but actually the build tools of ChromeOS. So there's this whole niche of software that most people aren't familiar with, and it's operating system build systems.
Yeah.
Not many people play in this space, and there's a handful of good ones. Debian has a really good build system. And there's a number of embedded ones. Yocto is one that's emerged in the last 2 years. But the thing that we liked about the ChromeOS build system was it was able to target different platforms, and platforms were like actual physical laptops that ran ChromeOS. In our case, platforms are like AWS, Google Compute, Physical Gear, OpenStack, VMware. And so we needed something that was able to target all these different platforms because each of them have different minor operating system incompatibilities and needs. And so we saw that what we needed was an operating system, build system, that allowed for this kind of targeted thing, which is something very unique to embedded software. And we were familiar with a lot of tools in ChromeOS's thing. They use Gen 2 as the underlying build system. And so we ended up going there. We look nothing like ChromeOS at this point, except for our update mechanism is very similar to ChromeOS's. This atomic update mechanism, very similar. But we don't have the advantage of having complete authoritative control over the hardware. So we've had to do way more work than ChromeOS does on like making the bootloaders work and all this stuff that begins all the way at hardware. I wish that I had full control over firmware and servers. I feel like every kernel engineer does. Like, we want faster boot times, faster. Anyways.
No, that's kind of cool because you've got your like embedded background where you've got this like atomic OS level build stuff.
Yeah.
But you're talking about someone else's hardware now. You're talking about Amazon's or Google's or the platform, actually. Yeah. So there's a mix of letting go of that control and also having to worry about things at a very low level.
Exactly. Yeah. So that's the story of with how we got through ChromeOS, and kind of the initial motivation for CoreOS, this consistency and security thing. And it really came out of running, 5 data centers system at Rackspace where we actually had one of our entire data centers go down because we forgot to do a kernel update on that particular data center. And these are things that are really hard to think about and remember unless they're automated, because as you scale from 1 or 2 machines up to 50, 100, 1,000 machines, thinking about, oh, did I apply the security update or did I apply that kernel update, it's just too much cognitive load.
Right.
And so you need to start automating these things more and more.
So this didn't come out earlier, but this immediately seems like this atomic update system and build system for operating system sounds like it would be extremely useful for the IoT space, right?
Yep.
You have to worry about these. CoreOS is really lightweight, is that right?
Yeah, for sure.
You can use it on lots of different devices, or?
Yeah, so CoreOS, we have a ongoing port to ARM. It boots, not everything's working, like our rollbacks and that sort of stuff. And then we have obviously our AMD 64 port.
Which is what, like, most servers?
Yeah, most servers are Intel AMD based. It's like some ridiculously high number, like I'll try to quote something, but it's over 90% of the market. Right. And so, but a lot of people have embedded systems that use those Intel processors. So we've seen people using CoreOS in like storage systems and network systems because they, like, similarly, IoT has this necessity for consistency and secure updates.
Mm-hmm.
And so
without cognitive load, because there's 50 billion.
Yeah, exactly. Like you sold 50,000 of them, hopefully, and so you'd like to be able to have that same property. And so, yeah, I think IoT essentially over time will start focusing less on these like one-time throwaway things like my light bulb, and actually focusing on, we need these same properties, and my light bulb at some point is probably going to need a security update because it's talking to Wi-Fi and like, yeah.
Right. Or suddenly it gets a new color or something.
Right.
Yeah, back from the home base. What you're handling a lot of the problems that developers don't have to handle now.
Right.
But that raises a bunch of new kinds of problems because there are opportunities for building distributed applications, right?
Yeah.
So now you have to think in different terms about your application because you can put them all in a lot of different containers. And are there any pieces of advice you'd give to application developers who now start thinking in distributed ways? Any basic ideas or concepts? And the most important one I know is like something's going to fail at some point, right? But I just want to talk about it.
Yeah. So unfortunately, the uptime and consistency of Google-like infrastructure doesn't come for free. Mm-hmm. One of the things that you have to start thinking about is failure domains, and we've spent a lot of time thinking about this at CoreOS. When you have a complex system, inevitably parts of it are going to fail, and so applications need to start thinking about, well, what happens if I'm unable to talk to the database for 30 seconds? What happens if the DNS is out for a few seconds? What happens if, etc.? And so designing for these types of failures is something that's ongoing. Now, the advantage of designing for these failures is that we're able to start doing things like upgrading each level of the stack, where before we'd have these very complex multi-day, multi-team sort of deploys. We're going to move from Debian 6 to Debian 7 this week, and it's just a big stress on everyone because that affects the application and it affects the operating system and it may affect the hardware.
Or you just don't update it.
Or the state of the art, which is arguably like install it, don't update it, and quit the job before somebody has to update it. By separating out these layers into kind of having contracts between them, you understand the failure domains of those contracts, but then we start to get into these lower stress situations where we're able to upgrade the operating system underneath the application, or we're able to take down a copy of the application because we understand there's 5 other copies of the application running, and that the load balancer will help take care of that. So just building resiliency into each level of the system requires thought, and it requires some thought that a lot of us haven't spent time doing. It's hard. Like we build applications still where we have to have a couple-hour meeting on where are the failure domains, what happens if this is down, etc.
Right. It means this abstraction going along a couple of different dimensions, right?
Right.
Not just what kinds of APIs are talking to what language, but also what's okay with me leaving. Do you find the CAP approach helpful for this, or is there a better way? Or
yeah, I think CAP, which is the consistency, availability, and partition tolerance, is a reasonable approach. Practical terms. So we have a product, Koi.io, and that is a product where people are able to build and download container images. So this is a very practical example of the CAP theorem. So one of the things that we would like to give users is the ability to have an audit log. So every time somebody pulls down a copy of your software, we can record, the IP address and the user and the API key used to pull that copy. Because you may care, you may want to know and do an audit of where's our software going, which host was it pulled down to, which users had access. So in order to do this, you need a strongly consistent system. Every time that I do a read, every time I want to copy that software, I also need to do a write of who read that.
If it's a break in the audit log at all, then it makes no
sense. Right, yeah, exactly. So this is really important for, like, say, your enterprise software. You may have some security-sensitive software or something like this. So in that system, consistency really matters. On the other side of the spectrum is, like, say our image for etcd or our image for Apache HDBD. Consistency is less important there because it's open source software. It'd be great to know how many users pulled it, but we really don't care about their IP address or what their username was, etc. We just really want a rough count of how popular is this thing. And so on that side, we care more about availability. We care about, like, say our database is doing a leader election and it's not able to accept writes. Well, we certainly still want to give the user their copy of HDBD. Maybe our count will be off by 3, 4, 5, a dozen. That's okay. We want to make sure that the poll is still available. And partition tolerance really is one of those non-negotiable things. Like, you either have a CP system or an AP system,
right.
And so everything else is sort of useless. So it's really like the trade-off of consistency and availability right. is the trade-off that a lot of us just have to design around. Do you fail, or do you kind of fall back and say, you know what, this information isn't 100% accurate, or it's not 100% consistent, but I'm going to fulfill your request anyways.
Any, like, final message for our readers about CoreOS or about containers, or just anywhere to check out for more information? Or?
Yeah, so the space is rapidly evolving. I think that the container is a very necessary and interesting part of this. I think a lot of people get it, though. They understand why the container is important and why they might want to use it inside their infrastructure. I think the thing that people have had less time to kind of fully understand and play around with is how these containers enable building infrastructure in this very scalable, Google-like way.
The Giphy thing that you were talking about. Google infrastructure for everyone else.
Right. So building systems that are fault-tolerant, easy to deploy, where I can focus on my application and less on infrastructure. So as like a parting thing, I think a great thing would people check out CoreOS.com. In the documentation section, we have really fast ways of getting up and started with Kubernetes, which is an open source project that Google introduced for building this sort of style of infrastructure with containers, but for distributed systems. Sort of up-leveling the conversation of infrastructure past virtual machines and talking more about application infrastructure. And so people can get up and running in like 10 minutes with a Kubernetes cluster on their laptop, or if they want to spend some of their employer's money on AWS, or also bare metal guides. But really fast way of just getting to the command line and getting to the nuts and bolts of how you deploy a multi-tier app in just a few minutes and understand the life cycle of those things.
All right. Well, thanks a lot.
Yeah, for sure. Thank you.